Hello everyone, this is Amy. Well, I was preparing for my high school entrance exam, so I didn't have time for a new video. But anyway, this is our new video series about geometric algebra. You can actually find a lot of videos on geometric algebra online, but actually, some of them seem very intuitive and understandable. But the key to a new mathematical subject is to learn about its foundation. And the foundation of geometric algebra is exactly linear algebra. Some concepts in geometric algebra may be abstract, like the ones in CGA, SDA, or something else. They can be fully visualized, as well as the Euclidean space. So it is very significant to first learn about this foundation. The first subject today is about vectors. Vectors is something we'll usually meet in geometric algebra, and it's the most fundamental and useful tool. First, what is vector exactly? In linear algebra concepts, it's defined along with a linear space by the following 10 axioms. An axiom is a statement that is true but without a proof. As you can see, this is how we define a linear space and a vector. Note that a vector is an element that belongs to the set, a linear space. But not all sets are linear spaces, because they're defined by the 10 axioms. The 10 axioms are about vector addition and scalar multiplication. As you can see, you might think it's pretty long and complicated at first, but actually it's not really hard to get the idea. It just tells us what kind of mathematical objects can be vectors. For example, functions, matrices, and anything else, as long as it satisfies the 10 statements. And from this definition, you can see that vectors are not just arrows as we think in the traditional way. You might be asking, so why do we actually sometimes think vectors are just arrows? Because arrows is a special kind of vectors. Vectors as arrows. We now set up our definition of arrows in a two-dimensional plane, which is exactly a linear space. Now we give our arrows a name, that is 1 vectors. 1 vectors has a magnitude, that is length, and a direction. 1 vectors with the same magnitude and direction are considered equal. Note that we don't need the 2 vectors to be fully overlapped to let them equal. We can simply let the 2 vectors parallel, because that way, they also have the same magnitude and direction. And that is why we say geometric algebra is coordinate-free, because it didn't need a coordinate system for vectors. And that is pretty useful in geometry and its applications. And the sum of 2 1 vectors is defined by the tip-to-tail triangle law as shown in animation, just like how we describe the total displacement of an object. It is pretty understandable, right? Just you first get a origin of 1 vector and then point it to the final point, and that is the sum of 2 vectors, or even more. For scalar multiplication, kx means stretching the vector x to make its length k times larger when preserving its direction. If the scalar term here is a negative number, it means turning the 1 vector x direction to the opposite side and stretching it b times longer. If there are 1 vector exists, denoted by this 0 such that u plus 0 equals to u. And here we have the additive inverse. With these definitions of 1 vectors, we can just simply say 1 vectors are a kind of vector. Note that here we can say arrows are vectors, but we cannot say vectors are arrows because vector is a very general concept. Now let's carefully study this special case of vectors. We haven't fully finished the construction of our linear space. We have only defined its elements. So what is the foundation of 1 vector's linear space? Just like a coordinate system in analytic geometry. For this, we can just consider what a coordinate system do in analytic geometry. What properties do they have? First, axes are perpendicular to each other. Or you can say they're orthogonal. The term orthogonal is pretty similar to the term perpendicular. We can just say they share the same meanings. Then, the coordinate system defines the unit's length. Also, it provides a coordinate representation for all points in a space. And that's exactly what the special vector should do. These vectors are called bases. Here, actually, basis refers to orthonormal basis, which is a more accurate term for this. Now, let's consider what vectors similar to the coordinate system should do. The two vectors or more, depending on the dimension, are perpendicular, that is, orthogonal. And the two vectors' magnitude is 1. We can say they share the unit length, or they are normalized. All vectors in the space can be expressed by a sort of combination of these vectors. Now we need more concepts to define what is actually a basis. Linear dependence and independence. Here comes a set of vectors in the linear space V. We say these vectors are linearly independent if the only way to satisfy the equation is by setting all the scalars to 0. If we can find a set of scalars, not all 0, that satisfies the equation, the vectors are linearly dependent. Yeah, this seems a little bit abstract, right? Actually, it means something very simple for one vectors. Let's think about what one vectors should do if they are linearly dependent. If they are linearly dependent, the only way to satisfy the equation is not by setting all the scalars to 0. That means stretching the vectors can get the same result as the other, and that would imply that they should be parallel, or just overlap, no matter the magnitude. Then they should be linearly dependent. If they're linearly independent, they should not be parallel. Also, the algebraic form here has a special name called a linear combination. A linear combination here, you can see, involves multiplying each element by a scalar and calculating the sum. A coordinate system should give a coordinate representation for all points in a space. And that's exactly what the vector should do. The next concept we're going to talk about is span, or in other words, generate. If every vector in the vector space V is a linear combination of some vectors. For the C in here means real scalars, and V in here are vectors. Then we say the vectors span the linear space V, and the set of vectors is the spanning set of the space. Something that spans the space should give a representation for all the vectors in the space. And if we combine the two, we form a basis. A basis is a set of vectors that are linearly dependent and can span the space. It turns out that a basis, orthogonal and normalized, of a space can replace the coordinate system. It is called the orthonormal basis of the space. But is that all for the geometric algebra? We only have two elements in the basis set for now. And here is the key to geometric algebra and what makes geometric algebra a convenient mathematical tool. We can indeed multiply vectors by scalars, as mentioned by the scalar definition. But what about vector times vector? Now we define inner and outer products. In linear algebra, there is a general definition for inner product for all spaces. An inner product on a real linear space, V, is an operation which assigns to each pair of vectors, U and V, a unique real number that satisfies the following. Here comes the commutative law, distributive law, and we can take out the scalar k, and we have 0 or positive output. In geometric algebra, we have a very special definition for inner products. Well, I mean in the one for two-dimensional Euclidean space. This can be very convenient because it shows how much the two vectors overlap, as shown here. We can easily prove, one by one, that the inner product we have defined is exactly a kind of inner product in linear algebra. Next, the outer product. The outer product is a very special kind of product. You might know the cross product, but this one is just more general. It can expand it to all dimensions, not like cross product. It can just be defined in 3 dimensions or some special dimensions, but not all. An outer product has a very simple definition. U wedge U equals 0, where wedge denotes the outer product. We can also call it the wedge product. Here, an outer product measures how much the vectors are linearly dependent. An easy example is when we calculate U wedge KU, we can get 0 because they're linearly dependent. We have a very special rule for this product because it doesn't have the commutative law for multiplication. For vectors U and V in the geometric algebra, we have U wedge V equals to negative V wedge U. This is called anti-commutative law. One of the definitions of the wedge product is the parallelogram definition. An outer product of two 1 vectors gives us something called a bivector, which can be considered a parallelogram. The geometric product, which is very famous in geometric algebra, is defined by inner product plus outer product. If you know about the concept of complex numbers, you may find them similar to this, because complex numbers sums a real number and an imaginary number up. But they're not the same thing, just like what a geometric product do. It sums up a scalar and a bivector, which are also not the same thing. Today we have talked about one vectors, bivectors, and their special way for visualization. This algebra is called a vanilla geometric algebra. A vanilla geometric algebra, or VGA, for a two-dimensional plane is spanned by the bases, a scalar, two one vectors, and a bivector. Note that we have more bases in our set, a scalar and a bivector. This is very different from the common linear space in linear algebra, because we have a new object, a bivector, defined by an outer product. That is what makes things very different, as we can see next when we come to the applications of the algebra. This VGA can be written as CL20. This is called the signature of a geometric algebra. Let's come to the very important topic today, the applications of VGA. Why do we use a VGA? Why do we construct it? And why is it useful? We come to its application, grade separation method. In GA, grade means the dimension of the element. Scalars, vectors, bivectors, trivectors, four vectors, and so on. Because the geometric product gives us a lot of information, the multidimensional information provided something more than the traditional representation. Take a very easy example, motion with a constant acceleration. Before we start, we should review the very basics of this kind of motion. Let's come to an axiom. Know that physical laws are often considered as mathematical axioms. We have two formulas here, where S denotes displacement, V denotes velocity, and A means acceleration, T refers to time. From these two formulas, we can derive a new formula. We can prove this by turning the vector form into a scalar form. That is to separate the vector formula into the basis term. So we have two scalar equations. For the scalar equations, we can draw a graph for the function. It's a linear function, and we need to calculate the area below the function. From the graph, we can quickly get the answer. When we solve problems here, sometimes we don't need the variable t. For convenience, we need to get a new formula without the variable t. Let's try to derive it. First, you may pause the video and give it a try by yourself at first. Maybe you can try out the scalar one at first and compare it with the geometric algebra method. See what's the difference. We can define a divide by vector operation, a over a squared. A squared is a scalar because we're taking the geometric product. A which A is 0 by definition, and A dot A is also a scalar by definition. Hence, from the first formula, we notice a divide by vector form. Substitute it to the other equation. Then we expand the formula, multiply using the geometric product A on the left side. A scalar equation and a bivector equation. We can separate the grades, the scalar terms and the bivector forms. Split it into two equations. And then we have the results. The scalar part may seem familiar if you have learned motion with a constant acceleration. It's a very basic equation, but a bivector equation is not that familiar. Now we can actually use the bivector equation to see what it really means. We can draw that. We're using the vector expression for the motion, so we can use it in any motion with a constant acceleration, even if it isn't linear. The projectile motion is a very good example for this. It is not linear. When we ignore air resistance, we can see that the only force acting on the particle is its gravity. From Newton's second law, we know that the constant gravity gives a constant acceleration. Hence, this is exactly motion with a constant acceleration. The parallelogram formed by V0 and V, S and A share the same magnitude and the same direction. This forces the four vectors to lie on the same plane. It shows the geometric relation between them. That's why geometric algebra brings us a new view for an old subject. Grade separation method is something that needs some practice because it's very different from the traditional derivation. If you want to practice more on these concepts, test your understanding, or try to do more grade separations, you can click the link in the description to find the exercise problems I have created. Anyway, thanks for watching!